Wow. You're welcome once again. Yes, last week Thursday, we started our discussion on linear regression after we finished with correlation. Now I want to wrap up the discussion today. For the benefit, I can see that the house is fuller. Maybe I wouldn't know, maybe we may have to get opinion poll after this meeting. If people actually prefer 7 o'clock, maybe it's more convenient, because I'm sure many people have been trying to catch up with the lecture before, and maybe they were not able to make it. And a lot of people said, oh, we didn't know that it started by 6, they came late. So let's quickly go on to the discussion of today. For the benefit of people that are joining for the first time, that were not around last week for the first discussion on linear regression, I want to maybe just quickly go through as fast as possible to go through the initial discussion, then we continue. So we talk about regression is a historical anomaly. It's an historical background which is very, very interesting. It was coined by a man called Francis Galton in the 19th century to describe a biological phenomenon. And the phenomenon was that the height of descendants of tall ancestors tend to regress towards normal average. This phenomenon is called regression towards the mean. It simply means that the average value of y, that is y, which is the independent variable rather, is a function of x, that is the change in x, which is the dependent variable. But you'll get to understand now later. The word regression sounds like go back in some way. Reduce the volume of that. The term has appeared in early writings since the late 13th century and derived from the Latin word regressus, which means to return. It is used in different fields with different meaning, but in any case, it is always referred to as the action of regressing. In philosophy, regression is used to indicate the inverse logical procedure with respect to that of the normal, demonstrable, or indisputable truth in which we proceed from general to particular. So in reality, regression means go back from the particular to the general, or from effect to cause. We look at the effect of something and go back to what are the causes of this thing. And it's very interesting that it marks the climax of research study nowadays, because most of the time when you have a research question, you want to know factors that are responsible for that particular research question, so that you'll be able to profile and give recommendation. That if those recommendations are carried out to a certain extent, you should be able to solve the problem. You're going to see by time, for those of us that were part of the workshop on linear regression, correlation and linear regression, it was very clear that the regression is just the answer, because no matter any the type of initial analysis you did, you try to look at do chi-square t-test, whatever you call it. So you may see gamut of factors that are associated with your outcome variable. Until you do multiple regression, you may not be able to know, because there are some confounders. Some of them confound for one another. For example, now, sometimes you are studies people of maybe between maybe around 18 years to around 40 years, and you are all maybe 15, just 18 to around 40. Okay, most of them when we study women of reproductive age group between 15 and 45, and you realize that age something increases with age, and it increases with level of education. You know that one may be confounded for one another, because the person that is older than 20, or older maybe 30 something to 40, is more likely to have had first degree or postgraduate degree than the person that is 20. So when you see an attribute that increases with age and increases with education, you cannot categorically say, oh, Both education and age are factored in that sense. Somehow, one may be hiding under the other until you do multiple regression before you can now know which is the factor. Very, very important. So you move from effect. The effect is the outcome measure. You now try to look at what are those factors that are responsible for this event. You try to screen those factors or move from condition to the condition. So that is what regression means. And in statistics, the time regression, as I've said, has ancient, origin and very, very special meaning. I've already made mention of this man, Francis Gatti. He was a geneticist, but he was more than a geneticist. He was a geographer. He was a philosopher. He was many, many things. In those days, that was the normal way of life for those who that were educated. They tended to dabble into many fields. So this man was a cousin of Charles Darwin, the person that proposed the evolution, the propounded evolution theory. He was cousin to Charles Darwin. And after his work, Gregor Mendel continued his work. So he was, one of the pioneers of this genetic theory before even Gregor Mendel picked up some of those the work. Then before people like Watson discovered the DNA, the structure of DNA. So and many, many things like that. So in 1889, this man, Francis Gatti, published an article in which he demonstrated how every characteristic of an individual is inherited by their offspring, but on an average to a lesser degree. That is, a particular characteristic is inherited by your children, but not everything to a lesser degree. For example, children with tall parents are also tall, but on an average, their height will be comparatively less than that of their parents. The same thing with children that with short parents. They will be relatively short, but they will still be taller than their parents. This phenomenon also graphically described is called regression. They now call it because they plotted the graph, regression towards the going back to the normal in the population. You will get since pick the meaning very well. Since then, this time has lived on to define this statistical technique called regression. In Gattin world, this corresponded to the concept of regression towards mediocrity, and the name of the statistical analysis. What it just means that whenever, if somebody is extremely tall, or a parent is extremely tall, or extremely short, so the children will be, for the tall parent, the children will be tall also, but they will not be as tall as the parent that is extremely tall, because he's trying to go back to the normal in population. Just like if a parent is extremely short, the child will be relatively short, but not as short as the parent. Now, the Gattin universal regression law was confirmed by Carl Pearson, who was a student. So Carl Pearson, the person that first of all described chi-square, and you made the most popular chi-square is named after him, Pearson chi-square. He's regarded as the father of mathematical statistics. He was the first person also to describe the Pearson, the correlation from covariance, and that is why that Pearson correlation is named after him. But however, it was his teacher, Gattin, that first of all coined the word correlation, but Carl Pearson took the word forward. He collected more than, that's Pearson now collected more than 1,000 height of members of family. He found the same thing his teacher found. Average height of the children from a group of short parents was greater than the average height of their father. The same thing, average height of the children from a group of tall father was lower than the average height of their parent. Can you see? That is the height of the tall and short children were regressing towards average height of all people. So if the parent was extremely short or extremely tall, the children would be tall or short also, but not as extremely as they will try to get back to the normal in the population. That is going back. That is the meaning of that word regression. Now, we have finished with the historical background. So regression is a way of predicting outcome variable from predictor variable. That is, whenever you have your research question, that variable that describes your research question is the outcome variable. Because all you are looking for is what are those things that lead to this thing. What are those things that lead to this? For example, if obesity is a problem in the society, obesity is a problem. When you are studying obesity now, you try to look for what are those things that contribute to obesity. If obesity is a problem, you want to know what are those things that contribute to obesity so that you do something about them. And if you give recommendation today to reduce the obesity, then your study, you are not looking for what obesity causes. You already know that obesity causes problem. If you want to know what a particular thing obesity causes, in that case, obesity is not the research question. That particular thing obesity cause will be your research question. And apart from you looking for what obesity, how obesity causes that, you have to now do your literature and also your research more. You look at other things that cause that problem. Because if you don't do that, you discover that obesity may give impression that obesity is causing a lot about that problem. But there may be some other factor that are hiding that even contribute more than obesity. So in that case, you have to now look at, apart from obesity, you have to look at other factors that may be responsible for you to be able to quantify the effect of obesity and also quantify the effect of the factor and also list the most important factors. So that is why if you are looking for what obesity causes, your research question is not obesity, it's that particular thing obesity causes. So when something is your research question, don't look for what is causing, but look for what is that thing called that is causing that thing. And that is why regression is the last resort to answer the question, because when you have a research question, you may have a particular reason to suggest that a particular thing is causing it, but it may not be only that thing. So that's why you have to now look for a lot of factors and do your literature review. And when you now look for a lot of factors, you study them on their own. Each of them may be contributing to the outcome, but you may want to know some may be hiding others the other. So in this case, you are going from the effect to cause. So you are trying to predict outcome. It may be from one variable, exposure variable. That outcome is your dependent variable because it depends on other factors. The other factors, they are independent variables. You can call them explanatory variable. You can call them factors. You can call them determinants. You can call them exposure. While your outcome variable is also called dependent variables. The factors are independent variable. Exposure, factor, determinants, explanatory variable, all of them is the same name. So the word dependent and independent, most of the time, is people that get involved in experimental research that actually, because when they manipulate, they now feel, okay, that particular outcome variable, it depends on the exposure they manipulated. They have done something about it. That's why I say it depends on it. That is why the exposure they manipulate is called independent variable. Why the outcome they are measuring is the dependent variable. So they use the word a lot, the experimental researcher, but it means the same thing. Outcome, dependent, or response variable. Those are the names. So the outcome, you can call it dependent variable or the response variable. Why the exposure, independent variable, the exposure, the factor, determinant, explanatory variable, factors. Call it many things. That one has a lot of names. So most of the time, it's usually more than one thing that will lead to a particular thing. And the work of the regression is for you to know what are those factors and grade them according to the importance. So when you are predicting the value of an outcome from one independent variable, that is simple regression. Simple. So I don't know why they don't call it single, because if you say single regression, but it is they don't call it single, they say simple. So only one factor. I know that in regression, only one variable you are predicting. You are not predicting more than one. You are predicting only one variable. It's your outcome. You don't have more than one variable as the outcome. But you can have one exposure, which is independent, or many. So when the exposure is only one, it's called simple regression. And when it is more than one, it is called multiple. So if they call this more than one multiple, why didn't they call that one simple? Why did they call that one single? Why did they call it simple? Okay, if they decide to call the one simple, why didn't they call this one complex? That's just the name. Single and multiple. Simple, not single. Simple and multiple regression. Simple, one exposure variable. Many exposure variable, we call it multiple regression. So, and whether it's going to be, if the outcome is continuous, quantitative, compounded, and continuous, that is linear. So you have simple linear regression, multiple linear regression. So here we are discussing linear regression. So if the outcome is categorical, that is logistic regression. So we'll be discussing logistic regression next week, even maybe starting from Thursday, because this weekend our workshop is going to be on stratified analysis and logistic regression. We can predict any data using the following general form. So in trying to predict, imagine you want to predict, say you predict, if you want to predict something, that's what they are trying to see what the value of this thing be, provided we have the value of the exposure. That is the meaning of prediction. So if for you to predict, you must be able to represent that particular thing you want to predict by a model. And in statistics, just like it's a branch of mathematics, you build a model to predict. And the model can be in form of equation or in form of graph. But in this case, even both graph and equation mean the same thing. That is, you can represent the model with equation or with graph. It's just to have something that show it, but it's not the real thing. It's just like if people want to build maybe church now, they want to build a new site. So they try to look for something that represents like a model, build a model, so that people have to be able to predict it. Because if you don't build a model, you may not be able to predict. So when they will now build a model of the church and now come and show people. That model, by seeing that model, cause people to release their money to build the church. So at the end of the day, it's the model that is able to predict the church. So it's just exactly the same way. So the outcome variable you want to predict, you now build a model. That model you use the exposure variable to build that model. But if you look at it, I say outcome is equal to model plus error. The issue of just I'm talking about, if by the time people put money and they finish building, you may say that what they build may not be exactly like the model. So that shows that the model was not able to completely predict what that building will be. So the difference between the outcome and the model is the error. So that's just in a graphical sense. But let's just move further for you to be able to conceptualize it. Now, we want to quickly look at how this model is being built. Now, I've already said that you represent this model, in mathematics, you represent by graph, which is like a pictorial form, and also you can represent by equation. So the linear regression signifies that if you want to predict a particular variable, it means that you are able to quantify that variable is a quantitative variable. Now, if there is an increase in the exposure variable, there will be an increase in the outcome variable or a decrease. It can be in both ways. So it means that if this outcome variable increased by 2, maybe the exposure, if the exposure variable increased by 2, maybe the outcome variable will increase by 3. If the exposure variable increased by another 2, the outcome variable will still increase by another 3. That is a linear relationship. And that is why correlation and regression are related, because the correlation look at the degree of linear association, that is, has to do with quantifying something. So if this one, as this one increases, as the exposure increases, the outcome is increasing also or decreasing, because it can decrease, it can increase. If there is any of this one, that shows that there's a linear relationship. Linear in the sense that it will continue like that. But if it's not a linear relationship, it may one increase as the exposure increase, the outcome can increase. As the exposure increase for that, the outcome can decrease. In that case, it's not a linear relationship. Or if the outcome, the exposure decrease, increase, and the other one decrease. If it increase further, it can start increasing. That's why there is no linear relationship. And that one, when you are, that's where you are talking about curvilinear, or there's a curve. In the example, is a good example is quadratic. In quadratic, something is increasing, reaches if we start turning down. But here, the simplest one you can use to predict will be a linear. We are starting with linear. So that is why the word linear regression. So you can have curvilinear, which will be an extension, but the simplest relationship is linear. And in that linear relation, if you are from the word linear, if you are to build a model, a diagram, you are not talking of both of them increase or decrease. You are talking of a straight line. So that is what brought a straight line and the equation. And this straight line, this linear relationship can be represented in a diagram like a straight line or in an equation. So statistics are borrowed from mathematics. No, statistics is a branch of mathematics, but I can tell you that it's not mathematicians that develop statistics over time. The people that develop statistics were the people that needed most. People, biologists like you, and social sciences, they were the people that developed statistics over time, although they borrow from mathematics. So now, this slide is talking about equation of a straight line, pure mathematics, this slide. So I said we discuss it, we're going to see the next couple of slides, will now show you how statistics borrow from this equation of a straight line, which is mathematics. Now, the shape and position of a straight line is defined by, because when you draw a straight line, there are two things that define the straight line. What is the shape of this line? Then what is the position of this line in geometric space? Just like any other thing, just like if you say that, oh, where's your address? They want to know where your office is located as per address, where it's located. And they want to see how your office is. So it's the same thing. So the straight line is defined by what is the shape of this straight line and what is the position in geometric space. Those are things that define straight, two things that define straight line. Those two things, the shape of this straight line is defined by the gradient, how slopey the line is, and why the position is defined by the intercept, where it crosses the axis. But for the case of equation of the straight line and regression, we are not more interested in where it crosses y-axis, where that graph crosses. You know, when we talk about y-axis now, you know, we are using a straight line to look at relationship between two variables, and one variable is on the horizontal, another variable is on the vertical. Now, when you use straight line in this way, it's not like correlation where you just say, okay, two variables, they correlate. There's no dependent, there's no independent. Both of them, they are just two variables. But in equation of a straight line and regression, I borrow from it, there is outcome, there's exposure. That is, there's dependent, there's independent. So by convention, X is the independent, the exposure, while Y is the dependent, the outcome. And the X is usually along this horizontal and Y is along the vertical. Is the convention. Just to, that is, to make it easy, that is the convention. So if you look at this now, when you see a straight line now, this straight line, two things that define this straight line is the shape, which is the slope, how slopey or how slanting. Another way name for slope is gradient. In fact, that is the word used in mathematics. Somebody is making noise. Let me, please, mute yourself, please. If you want to be talking at home, mute yourself so that it doesn't disturb others. Now, you will see that you see this line.
I want to move to the next slide. I will come back to this slide so that you understand that slope. That slope, because there are two things that define this straight line: the gradient, which is the slope, and the intercept. So in the other slide, the next slide, explain the slope very well. Slope means how slanty is this line. Then not how slanty alone. How does this slant from right, if you move from left to right, does it slant upward or slant downward? So two things about that slope now. We look at this first line. Because when you are talking by convention also, when you represent horizontal as x, which is the exposure variable, the vertical as y, which is the outcome, where both of them cross is the origin, is 0. So if you move from that 0 to the right, for the x, you are moving in positive direction. If you move to the left, for the x, you are moving in negative direction. For the vertical, which is the y, if you move upward above that 0, you are moving in positive direction. If you move downward, you are moving in negative direction. Having understood that, now look at this first one. It moves slant from the left to right upward. So it means that it increases upward like that. What it means is that if you look at it, as if you look at it, move in the same direction as both of them. Because if it moves from left to right upward like that, slope upward, it means that x is moving in positive direction, y is moving in positive direction, because the positive direction of x is right and the positive direction of y is up. So if it slopes from left to right and upward, so it's positive for both x and y. What it means is that as x increases, y increases. Both of them increases together. That is slope, positive slope, positive slope. Now, the second one is negative slope. Can you see? It moves from left to right, but it now move downward. So in that case, downward for y, it means it's reducing. But of course, to the right, it means decreasing for y. So what it means that as s increases, y decreases, and vice versa. It means that they move in opposite direction. If s increase, y will decrease. If s decrease, y will increase. That is it. So that is negative slope, because it's slant from left downward. That is negative slope. The third one, it's from left to right, but horizontal. It shows that, of course, s is increasing, but y is not increasing because there's nothing that shows that it's moving up. So y does not change when s change. It means the slope is 0. As you're going to see, when there's no relationship between two, it's like that. If there's no relationship between x and y, if x, which is the exposure variable, change, it just change for nothing. S is not moved. In y, rather, y is not moved. They show that there's no, so the slope is 0. It shows there's no relationship. So you can see that it is slope that is actually showing the relationship between x and y. As you are going to see the meaning of that slope, that gradient. Now, the fourth one is the undefined slope. This one is just a way to dodge the undefined. And the reason is very simple. The reason this undefined is that people are interested in y changing after s change, because x is the exposure, y is the outcome. So if we look at this one now, this one that is going upward, it means that x is not changing in one place, but y is going up, or either going or going down, but x is not changing. People are not interested in what happened to x, if y change or not. What we are interested in is the x is the exposure. What happened to y when s changes? So that is why this one slope 0 still makes meaning that there's no relationship even when x is changing. But this one that y is changing is undefined slope because it has no meaning for the equation of the straight line, so it's undefined. So when we are talking about slope now, we are talking of whether the slope is positive or negative or zero. I think we understand this. And it's the same thing when you are considering correlation. It's only in correlation you don't define anything as S and Y. Even though if you define as S and Y, there's no dependent or independent variable. Both of them are just factors you just want to see how they chain together. But this slope issue is still the same thing. You know, either positive, negative, or zero. Let's go back. So we have understood, but we have understood only one aspect of that slope. But the other aspect is how slopey. How slopey. If it's very, like for this one, look at change in S per unit change in Y. Let me just look at this change in X here, mean from here to here. X1, X to X2. That's the change. That's what is drawn there. Where is it now? Right thing again. Wow. Oh, the thing shifted. Okay. Sorry. Oh, so now I'm trying to, yeah, S2. Why this one from here to here? It means that Y1, Y2. You can see it's change now. But if this thing, so Y1, Y2 minus Y1, that is change in Y when S move from S1 to S2. But if this thing is small slanting like this, when you try to measure, you see that if you do it, you discover that there is per unit change in, okay, if you even draw it from the same place now, you are going to see that, can you see the same thing? You extrapolate it, you see that Y change more with this other line I draw that is more slopey. Y change more. So the more slopey, the more the gradient, the more change in Y per unit change in X. So you can see how slopey it is. We quantify the change in Y. And why the direction of the slope will tell you if it is it increasing or decreasing, the direction of the relationship. I think that one is very clear. So when we come to the intercept, which is where Y, the graph cross Y. If you look at where the graph cross Y, if you trace it back to the origin, X is 0. So where the graph cross Y, X is 0. If you look at where the graph, even the other one, where the graph cross X also, if you consider where the graph cross X, Y will be 0 also. Whenever the graph cross X, Y will be 0. But nobody is interested in the intercept of X, where it crosses X. It's where, because the issue there is that is change in X that determine change in Y. So the logic behind the intercept is when X is not even changing, does Y has value, because X may not be the only factor that is responsible for Y. So that is why the intercept of interest is Y intercept, where it crosses Y axis. And in that case, the value of X is 0. That is, when that particular exposure variable, if it is not there or is not changing, is not varying, does it actually affect? In that case, the Y also see a value. If it's Y is not changing, the Y has value. That shows that it may not be that S alone, that variable alone that is responsible for Y. There are many other factors that may be responsible. So you will see when you now put the Y, the M is the gradient, which is the slope. So then the C is the constant. So if you want to quantify Y now, you look at what is this change for 1 unit change in X. What happened to Y? What happened to, so what happened to Y? What happened to Y is that the unit change, the slope, the unit, that is this side over this side, which is called the Y, the X. In further maths, the Y, the X. Change in X over change in Y is a change, that is what per unit change in X, what change in Y, which is the slope. So if you really want to predict the value of Y, when you know for each change in X, what value of, so you multiply that what the unit change in Y times that value of X plus the constant, which is the value even when X is not there, Y has some value. So you have to add it to now know the real value. So that is why the equation of a straight line is Y is equal to MS plus C. That C is the intercept. It's called constant, and that is why in mathematics they call it C, constant. Constant just means that even when X is not there, that thing is constant with Y. Y, that thing is always there for Y. Y has a value even when the X is not there, has not changed. Y has a value. That is why they call it constant. So this Y is equal to mx plus C, the equation of this straight line. Now, please you can be chatting your question. Now, if you move to the next couple of slides, let me move forward. It's not changing. So, why is it not changing? Sorry. Sorry, let me reshare. Yes, we have explained this other slide on the slope. Now, let's look at what slope and the intercept actually mean. We have 4 graphs here that is showing slope and intercept. The upper two, the two upper graphs is showing positive slope, as we have discussed before, because they slant upward. The two that are below show negative slope because they slant downward from left to right. I think that one is clear. But what is I want you to see here is that look at this first one, the one for this side, this on the left side, the two for the left side, up and down. This first one, even though it's slant upward, but the intercept is positive because it's above 0 for y-axis, because we are interested in y-intercept and not x-intercept. Where it crosses y-axis is above where it crosses y-intercept is above 0. It's on the positive side of y. That shows that the intercept is positive. But look at this one below. The slope is negative, but the intercept is positive also. Can you see? Because it crosses the y-intercept as it's above the 0. But when you come to the right side, this first one up here, the slope is positive, but it crosses, the intercept is negative because it's below 0. It's on the negative side axis of y. So the intercept is negative. While this one down, even though the slope is negative, but the intercept is negative also. So the first graph now, slope positive, intercept positive. This second one, slope positive, intercept negative. The third one, slope negative, intercept positive. The last one, slope negative, intercept negative. So the slope shows the shape of the graph. I already said it before. Whether its slope is positive or negative, or is very slopey or not. Now, the intercept shows the location of the graph in geometric space, whether the intercept is on the positive side above the 0 or below the 0. So the intercept shows the location of the graph in the geometric space, while the slope shows the shape of the graph. Now, we are done with mathematics. Let's come to statistics now. You will see the same graph. Instead of writing y is equal to ms plus c, now write y is equal to a plus ba, or you can say bx plus a. So the a is the constant. for mathematics, the intercept. While the B is the slope, the gradient. Instead of M, in mathematics they use M. But this B, it is called regression coefficient. They say that we have already said it is change in Y per unit change in X. Change in the outcome variable per unit change in the exposure variable, or change in the dependent variable per unit change in independent variable. So you see that the slope is, this is what we call regression coefficient. And A is the constant, where the intercept, that is the value of Y, even when X is not contributing anything, Y still has value. So the regression equation would that be Y is equal to A plus BS, or Y is equal to BS plus A. Just like this. So it's just like they just change the notation. It's the same thing. Equation of a straight line in mathematics. It's now the same thing as regression equation in statistics. Now, how do you write the regression equation per se? When you are writing in real life, that constant also is a form of coefficient, but they call it B0. B0 constant. So if it's only one variable now, which is simple, the regression line, the other that variable will be, the coefficient will be B1. That variable will be called X1. Because the constant is B, the coefficient for the constant, the intercept is B0. That we now call the variable, that only one variable, B X1, and the coefficient will be B1. But if you have more than one variable, so the intercept is still there as B0, so B1 X1 will be for the first variable, B2 S2 will be the second variable. If you have up to 10, B3 S3, B4 S4, up to the last. That is why you say dot Bn Sn, as many as possible. So this first is regression equation, simple linear regression equation. The second one is multiple linear regression equation. Now, in real life, if you plot your graph now, you plot the value of X against Y, you will see that the equation, if you draw the line, you just draw the line. All of them cannot be on a straight line. All of them cannot be on a straight line. As you're going to see here, all of them cannot be on a straight line, as you see. So you will see that the line, some may be on line, but you see some that are up the line, other below or above the line. So the difference, that will be a difference. That shows that whatever, like for this line now, you are seeing, what for this first dot now, the predicted value will be, if you draw a perpendicular line to that value, that will be the predicted value. What is just telling you that there's an error, that's all. That is, there's an error in predicting each value. The distance between the line and the dot will be the error. And that is why in writing the model, you write it B0 plus B1 S1 plus error. That is, this first one is for the simple regression model, and this second one is the multiple regression model. You see, I have your B0, B1 S1, B2 S2, all to as many as possible, but there will be error. The error is where it's not able to predict it, and you understand it better. Now, we know that there will be error, but if you are to be given, look at two scatter plots now, to draw it, you will discover that if I give it to everybody to draw now, for each of this line now, the regression, because there are two regression scatter plots here. If I give you any of them or both of them, everybody will draw different line. Your line will not be the same thing. What you're going to draw manually, it will not be the same thing. So using manual method, we are talking of method of drawing the line. Instead of manual method, which will not be accurate. If you draw your line is not the same, how do we know which one is correct? Then if we now use a method we call method of least square. Actually, the best line is called the line of best fit. And that line of best fit will be a line. If you draw it And if you now look at the distance between each point and that line and square the distance, when you add it together, it will give you minimal value. What I'm saying is this, in essence. Let's say I give you this first one to draw now. All of you, about 10 of you draw different line. If we try to, for each of the line, each person draw, we now calculate the difference between each line and each dot, and now square the difference and add it together. The person that is going to give the smallest value will be the best line, because it's the one that is, in essence, is closest to all the dot, all the point averagely. You know, each point is where X and Y meet. It's for one participant in the study, that is the X and value of Y where they meet. That's what form the point. So when you draw a line now and you try to look at the distance from, because the one that are below the line, they have negative value, the one above positive value. When you square it, you add it together. The one that minimize, that have the smallest value will be the line of best fit. And that method to get that line of best fit is method of least square. That is, when you square it, it give you the smallest value ever possible. That would be method of least square. Now, you may say that how does it done? You know, drawing manually, that was those days. But now, computer will even draw it for you through the method of least square to give you the best line. Now, look at the way it goes. After drawing the line now, you will see that, of course, not all of them are on it. The distance, so you are having two values here. The value predicted by the line and the observed value. Observed value is the dot you are seeing. But if you now draw a perpendicular line from that dot to join the line, where it joins the line, that is the predicted value by the line for that particular dot. So the difference between the predicted value for that dot, which is on the line, and the observed value, which is that dot itself, is the error. Can you see? Observed value minus the predicted value give you the error. Now, if you look at it, it's for Y, because for X, because it seems it doesn't change, but it's the Y that has the observed value, because that line is defining Y, the value of Y, not value of X. For each value of X now, if you draw the perpendicular line, it doesn't change. The value of X does not change. There is the value of Y that changes from between that line and where that dot is. There's a difference. That difference is the error. Now, this is a simple linear regression model. After you have, can you see? It's showing the line and the dot and each the error. Now, you can draw your slope, perpendicular line here, then from one point to the other to calculate the slope. You now divide the slope now is changing Y or changing X, which is the B1. And the intercept is the constant, which is B0. We have already said that was B0. Now, how do you calculate it? We have a data set. This data set showing height and pulmonary dead space. The pulmonary dead space is this height of a child, of children rather, and pulmonary dead space. This pulmonary dead space is part of the lung, the airway that is not involved in gaseous exchange. All this from trachea to bronchus and some part of the alveoli that are not involved in gaseous exchange. So there's a hypothesis that okay, if the height of the child determines the dead space, so there's a relationship. So the dependent variable now will be the pulmonary dead space, and the independent variable, which is X, will be the height. So if you look at it, you will see, for you to calculate, from here you can calculate even the regression coefficient to really know change in Y per unit change in X. For you to even write your equation of a straight line, you can write regression equation for this data set. You can do that with R. Now, You know that change in dependent variable y. How do you measure change in dependent variable y? Due to x. That you, if you say that you want to measure change in y that is due to change in x, you can measure that by change in x that is due to change in y, or change in y that is due to change in x is measured by the covariance of x and y. Change in the x itself is measured by the variance of x. Change in y itself on its own is measured by variance of y. Change in x is measured by variance of x. The change in y due to change in x is measured by the covariance of x and y. Now, this is variance of x, this is variance of y. You know, you remember variance, sigma x minus x bar square over n minus 1. N minus 1 is the degree of freedom. And you can write it, instead of say x minus s bar square, you can write x minus s bar 2 times. The same thing with y, you can write it like this. But the covariance of both of them will be sigma s minus s bar into y minus y bar over n minus 1. Now, consider the if change in x is the value, change in x is the variance of x, change in y is the variance of y, change in y due to change in x is the covariance of x and y. Regression coefficient, which is b, which is change in y per unit change in x, that is divided by change in x, will be covariance of x and y over variance of x. Because change in x and y due to change in x is measured by covariance of x and y. But change in x is measured by the variance of x. So change in y per unit change in x will be covariance of x and y over the variance of x. And that is exactly this. If you divide by this is formula for variance of x. So if you now divide, you now change the you now mathematics change the division to times. Numerator here will become denominator. So n minus 1 cancel n minus 1. So it will give you this, and which is this is the formula for regression coefficient B. It can be written in a way, just a rearrangement, mathematical manipulation, just to so that if you are calculating, you can remove the effect of decimal. But this first one is the actual formula for you to be able to conceptualize. So you are dividing covariance by variance of x. You remember when we talked about correlation, it's actually standardized covariance. Covariance divided by the standard deviation of x and y. Covariance of x and y divided by the standard deviation of x and y. That is correlation. The regression coefficient is covariance of x and y divided by variance of x. It's not the standard deviation of x and y. So that is the difference between correlation coefficient and regression coefficient. Now, in that case, you are able to find the y, the slope. That is the slope. How do you get the intercept? Once you know that y is equal to a plus bx. So you can, since you have already gotten b, you now say, okay, now say, you can as well say mean of y is equal to a plus b mean of x. So if you have gotten b, you just say a, which is the constant, will be y minus bx. B mean of x. A is equal to mean of y minus b mean of x. So you can substitute and get a. That is how you can actually calculate the regression coefficient and the constant intercept mathematics with m. And if you run it, you get the same answer. This is what. So can you see now? The formula x minus s bar, just say s, you remove s bar, which is the mean of x. Y minus y bar, you remove y bar, which is the mean of y. So multiply the two of them, s minus s bar times y minus y bar. Then s minus s bar square, which is, so if you divide this, you summation, the sigma means summation. When you sum all this, you give you this, sum of this, give you this. So this over this is it. So the regression coefficient is 1.03033. It means that for a unit change in the height of the child, the pulmonary dead space changed by 1.033 ml per cell. And once you have gotten that, this one you can get the constant. Y is equal to mean of X in A is equal to mean of Y minus B, X. You substitute. You have already gotten Y. We have the mean of Y, mean of X. We're already getting B. Yes. So A is equal to input is minus 82.4388. 4388. If you have your question, you can start chatting. When we stop, we'll be able to attend. I wanted to put the record to there. Yes. Now,
good evening.
So please, somebody should not talk. You just chat your question. Don't ask question now. Just chat it. Now, that is calculation. Before you actually bother yourself much about what the mean of the value of P is and the value, she is what? The value of B, the value of A is. Before you can make meaning, after you have plotted, you have developed the model, the straight line, we have to be sure that it fits. Just like before you can say we are using something, you have to be sure that that particular thing is useful, is valid. It's just like you brought a machine to do analysis in the hospital, chemical analysis. Before you can be, oh yes, you are running your test, you are dishing out result, you are using it. You have to first of all validate it. Really know. They should try and use it to do some sample, which they have already done somewhere else before, to really know, is it actually measuring? Have they validated this case? Because it can be measuring something, it can be bringing wrong result for you. So, assessing the goodness of fit of that line, before even B and A can be so meaningful, how do you assess the goodness of it? Two ways. F ratio and R square. What does that mean? R square, the R square you are seeing is the same as correlation square. You square the correlation. They mean more than that. Apart from squaring the correlation, you can even calculate it from another two ways. Then F ratio means variance. Anyway, we have already, when we discuss analysis of variance, I often say the analysis of variance and regression is the same. They are the same. They are two faces of the same coin. ANOVA and regression are the same. Now, when you run your ANOVA, you see when you run your regression, you see ANOVA as output. It comes out as an output. And if you have a data set, you run ANOVA, you can run regression, it gives you the same thing. So the same result. Now, let's explain this R square. So you see the formula, sum of square model over sum of square T, which is R square. The F ratio, mean square model over mean square residual. What does it mean? Pictorially, be able to graph it here. By the time we explain this, to stop. Now, you see from what we have shown before, this second on this right side, you see this graph is familiar in the sense that this is the regression line we have just seen, and these different are the different dot are different values that are of the line. And we already said that it cannot completely predict it, so we now have some of them off the line. So the difference between each value and the line is the error. So, but you will see something. This is the same scatter, but this line you draw is the mean of Y. The mean of Y is drawn here if it's horizontally. If you look at this line and the value each dot and compare with the regression line, you will agree that the regression line is closer to each dot than the mean. The regression line is the model you have built, but the mean is a model that has been there. Is a crude model. Is the crudest model. Let me explain. Mean is poor for prediction. Is there. Mean is the value when no hypothesis is true. Mean is the value when there's no difference among different groups. For example, if somebody can just say, oh, all of you in this class, I want to know the average weight. You now calculate average weight, and that's, oh, the average weight is 70. That is average. Some weigh less than 70, some weigh more than 70. But that's average. If you multiply the average by the number of people in the class, it gives you the total weight contributed by everybody. So actually, how did you calculate the average? By adding all the weight of everyone, divide by the number. It's trying to say, okay, I'm gathering all the weight, I'm sharing it equally. It's just like somebody collecting money from everybody now, and I share equally. Collect different amount from different people, and I pull it together, and I share equal, and I divide by the number, and I give it to you. So it's saying that all of you are the same. All of you are equal. So mean is a crude model. In the sense that he does not, is a poor predictor. I usually give an example. Imagine you have a nursery school and you want to do inter-sport for your student, nursery and primary school. You now say, okay, you want the sportswear to be brought from UK, and your friend went to UK. They now call you, I'm here now. They are asking me, what is the average age of your student, so that they can know the type of the size they can give. You now call the head teacher and say, what is the average age of a student? That one has 7 years. Okay. Now say 7 years, so okay. You now jam pack 150 sportwear, all of them for 7 years with child. So at the end of the day, of course, some it will fit some as around that 7 years, but some it will be too big for some, because some are simply more than less than 7. It will be too small for some that are more than 7. So they have used 7, the mean average, to predict, but it's a poor predictor. Mean is a poor. So as you can see now, mean of y is far averagely, even far from each point. It's not as close to each point as the regression line. So mean is a model, crude model that is available even before your regression. It has been there. Then this is your own regression line, your own model you have built. So what you want to know is, how good is this model? So for you to know how good something is, you must be able to compare with something as standard. But you don't have any other type apart from this crude one. It's just like if somebody in the family, if a child is dull, you can, the other one that is a little bit better, you can compare and say, this one is better. You can compare, you even better. But that one may be dull also, but just as dull as the other one, say you are even better. So then if you have one that is dull and you now have, how do you know? You want to compare two. So if you want to compare the other, how the best among two, by measuring how they are better than the other one. So that's just what the mean is for now. So there's no other model to compare. It's the crudest model. So if you want to know if this, we know that this mean is a crude model, how better is the regression line? And how do you measure that? You just mean the variability to be explained is done by analysis of variance. Let me just tell you. And that is why we have given lecture on analysis of variance. So please, I want people to just subscribe for the, because all the even, let me just give you one expo. All our, for now, I don't know, maybe later, all our, even our lecture, our workshop, they are there, and you can access them through the site. You can access all of them through the workshop and all the, there are up to over 70 of them, the video, both the workshop and the lecture, they are there. And we are giving lecture and workshop on the ANOVA. For those of you that you have grasped what you are in the workshop on the ANOVA, we talk about its analysis of variance. So in order to know the goodness of it, is the analysis of variance also we want to do. The variability to be explained for the total set of this data is what mean the crudest model have. We can say it's the total problem to be solved. And how do you know the variability? If you know the distance from mean from each of these dots, and you square it, that would be the sum of square total. And the basis for this is very simple. If you remember when we try to calculate our variance, standard deviation, from the mean, you remove mean from each value, x minus s bar. You know that if some will be negative, some will be positive, because look at it now. X minus s bar means the mean. You remove from each value. So if you remove mean from each value, what will happen? The one that are below the mean, the value will be negative. The one that are above the mean, the value will be. So the distance between all these ones that are below the mean is negative. The distance between the one that are above the mean is positive. If you try to add them together, it will give you 0, because mean is in the middle. So the intelligent people, okay, they now square it. When you square it, it removes that's logic behind squaring. It removes the negative. So now, when you now square, it gives you sum of square total. So that is where you see what you see here. SST means sum of square total. Sum of square total uses the difference between the observed data and the mean value of y. So you remove the mean from each value and square it. It gives you the total variability you can explain. And it's the same thing in ANOVA. When you do ANOVA, the ground mean, the mean of all the group, when you add all the group together, every data set. The data set may be 3 groups, but you add everything. Let's say each of them 5, 5, 5, and there are 15. Instead of saying you add all the 15 together and divide by 15, it gives you the mean ground mean. You remove from each of them, it gives you the total sum of square. The same thing here. So the total sum of square here is the same thing as total sum of square in ANOVA. Now, if you come to this one, when you remove the value, the difference, the error, you know, the value of this regression, and remove from each of these values, give you the difference. You square it, it gives you the sum of square residual, which is ISSR, sum of square residual. It uses the difference between the observed data and the regression line. Now, what this total sum of square present is the total problem to be solved. Then this one is presenting what the regression line cannot solve. And you see what the regression line cannot solve. The model you build cannot solve. This is the total problem to be solved. This is what it cannot solve. So for you to know what it has done, what it has solved, you remove what it cannot solve from the total problem to be solved. So when you now overlap the two graphs now, you remove this sum of square residual from the sum of square total. It gives you the sum of square model, which is, it uses the difference between the mean value of the y and the regression line. That is, you remove this one from this, it gives you the sum. So this is the model. Now in ANOVA, we have already said that this sum of square total corresponds with the sum of square total there also. In ANOVA, what corresponds with the sum of square residual is sum of square within each group. Now, what corresponds with the sum of square model here is sum of square between group. And you know, when you add these two together, it gives you the total. Of course, you get this one model by removing this one from total. So if you add this and this, give you total. Just like the way in the ANOVA, sum of square within and sum of square between add up to total sum of square. Now, where does our R square comes in? Our R square, what it says that what can be explained by the model. That is what the model explains. The regression line explains is this sum of square model. You now put it over the total. You want to know the proportion of the total variability to be explained that have been explained. The proportion of the problem to be solved that have been solved. When you put this over this, you express as percentage, that's the R square. If you do it, or you square correlation coefficient, correlation, if you square, it gives you the same answer. And when you express as percentage, that is what we call coefficient of determination. Coefficient of determination is percentage variation in the outcome variable that is explained by the exposure variable. So if let's say 70%, it tells you that 70% of the y is explained by this x. So there are other 30% that we don't know what to explain it. But for this exposure variable, what it can explain 30% of this outcome variable. No, 70% of this outcome variable. Remaining 30% we don't know. If it is 10%, it can explain. You say, oh, this our x, so can only explain 10% of y. The remaining 90% we don't know. You cannot know that that type of model is not good enough if something can explain only 10%. So your research has only explained only 10% of the problem. The remaining 90% we don't know. So if you give a recommendation, it takes a mad person that ignorant people to go and be spending money on your wasting time on your recommendation. But of course, if he's giving something above 50%, 60, 70, 80, you know that yes, if something accounts for 70%, if you give me a recommendation, I will know that okay, if I can do this recommendation, I'm attacking 70% of the problem. Well, it's worth it to do that. But if something is less, maybe 20, 10, you are now giving a recommendation, I will now be spending money on that recommendation. So that is why you need to understand statistics. Sometimes people can tell lie with statistics knowingly or unknowingly. Some people can tell lie, they may know. Of course, they are telling lie. Some don't know, they are ignorant. They're telling either they know or don't know. If they give you lie and you are now making decisions based on lie, you are wasting your resources. And that is why I, for one, if you publish your paper, you give your recommendation, you give your conclusion. I would rather look at your methodology and look at the research and make my own conclusion. Then I can conclude. After all, you concluded from the result. Because sometimes you may misconclude unknowingly or knowingly. So it's better I see where you're. Number one, first of all, look at your methodology if your result is reliable. If I can establish that fact, I will now conclude for your result myself. If this is not reliable, I will not even bother myself by your result. That's just it. Now, you can see the R square now. That is this sum of square model divided by the total sum of square. That is what you see. Can you see? R square, sum of square model divided by total sum of square. Sum of square total. Now, the other one. We already said that this model is the one that explains the variability. Your research, your model has explained sum of square model. This sum of square residual is what it cannot explain. So if you want to know how good it is, if you divide, though it's not directly the sum of square model, you divide by the sum of square residual, you now calculate the variance out. The variance for this model, because how do you calculate the variance? Sum of square over the degree of freedom. You now calculate the sum of this variance for the residual. You now divide this variance for the model by the residual. You want to know how many times what you can explain is more than what you cannot explain. If what you can explain, you make it as your numerator, and the residual, the one you cannot explain, which is the error, make it denominator. If what you can explain far offset what you cannot explain, it will be greater than 1. Not only greater than 1, it will even be far greater than 1 and give you a value. If you give you something like 5, 30, 300, it's telling you that what you can explain is 300 times what you cannot explain. It's a good one. Or what you can explain is 10 times more than what you cannot explain. If you divide it, it's a good one. So that is F ratio. That is, when you divide what the variance You can explain over the variance, you cannot explain, which is the error. The model can explain over the one, the model cannot explain. If it's far bigger than one and far big, you know that the model is good. Or if the most reliable one, the best one is the R square. When you have the percentage variation, that once you are able to get big chunk of it, that should have this variable is the one that is responsible. You are assuming for 70% of this outcome. No, let's do something about it. If you give your recommendation, I'll be able to follow. So in multiple regression, that is the simplest example we just used is simple regression. In multiple regression, it's not a straight line. It will be a plane. Though it's a three-dimensional because the other one is two-dimensional, but this one is in the sense that the vertical axis is always the y. But the x now will form a plane if it is more than one. If it is one now, it's a line that is formed. But now if it's more than one, it's formed two lines at angle. So when you have two lines at an angle in succession, it gives you a plane figure. Like now, when you have two variables, now it gives you a plane figure that has 4 sides. So if it is 3, it gives you a plane figure that has 6 sides. If it is 4 variable, exposure variable, it gives you a plane figure that has a hexagon, 8 sides. I think we stop here. So the other one that just maybe a little bit, you know, it may be difficult for people to conceptualize unless you maybe you go and watch use the opportunity, go and subscribe and watch the video workshop video, because where we had a lot of time to explain and we even run the analysis there, so you can watch it. But this is just graphical. You can see now, you can actually, from what we have done, you can actually calculate it out and interpret it. So if you run it, so the workshop affords us opportunity of having the data and running it with SPSS so that we'll be able to conceptualize. I think we'll stop here. I want to entertain question. So there's no chat. Actually, that is very simple. Didn't see any chat. It was very simple. Any question? No question, unless if somebody, if you don't want to, you can ask your question. I'll be surprised if you have been following up, because
yeah, you know, I always ask my question. Yes. Yeah. Actually, I want to know. You said something.
Just wait a bit. Let me. I'm not hearing you very well. Let me check my what do I call it? My speaker. Okay, my speaker. Okay, go on.
No, this is just my own thinking, though.
Okay.
If you said R square, of course, in correlation, when you do correlation and you square it, you get the R. Abi?
Yes.
Squared. Am I correct?
When you square correlation, give you R square.
R square, yes. So, and what the R square in regression and that R, they essentially mean the same thing.
The R square,
is that correct?
Regression and R square also. Yes, it is even
correlation.
Yes, because correlation is related to regression. Two things you cannot regress unless they correlate. Yes, unless they correlate. Go on.
Oh, okay. So I was just wondering why you have to do regression when you now already know your R square. But now definitely you need more information after the R square, the F ratio and other things.
Thank you. And you know also that you will not even go just like a statistical significance does not mean clinical significance or any engineering significance or whatever significance. Now, there must be plausibility there. Now, it's not everything that correlates that you regress. You understand now? There are some things that they even correlate, they are not even related for anything. That shows that there's something else that is bringing them. It's just like somebody seeing you and somebody in this class now. And Dr. Balogun will be doing as if he doesn't know that lady or that guy. And they are in the same class. So, but the issue that you may the person, but there is a correlation in the size that both of you are in the same class. But what brought you together is the class. Is the person that the confounder that is the person that invited both of you. You understand me? So that is just it.
Yeah.
You can have correlation like that.
Okay.
It's just like they say that rate of suicide correlates well with sale of ice cream. What does that mean? The only thing that can bring them together is season. Maybe the season the ice cream sell most is when people also commit suicide. I don't know if you understand me now. So you will see that two things can even correlate that they don't know. But it's not possible for you to for two things to relate without correlating. You understand me? You cannot regress something that they don't even correlate. That is where correlation comes in regression.
Okay.
Yeah.
Okay. Thank you.
You're welcome. Any other thing? Any other one? Any other question? Okay, somebody chatted. This is like an answer. A candidate found 0% of a phenomenon in a control. This is like an answer. A candidate found 0% of a phenomenon in a control as against a comparison group. They still went ahead to do regression with dummy. Does this make sense? For that, you cannot, it's not possible because, one of the things that you cannot do because what is that attribute does not vary among the what do I call it? Among the control. If it does, you cannot use it. It doesn't because it has to have a value. Even if it's going to be low, there must be some variation. It should not be zero. So it's not possible. It's not possible. I don't know if you understand me now. It's not possible. You cannot do that. No, you can do the regression for that thing, but not for that attribute that is now zero on one side. Are we together? So the issue is at the end of the day, where you can see, but what will really happen is that you know what happened? It can only correlate if it doesn't separate them. Both of them are together, and what will now happen is that the attribute, on the other in the experimental side, there are some that have the attribute, there are some that don't have the attribute. On the control side, nobody have the attribute. So when it's correlating now, what will happen now? We combine those ones that don't have the attribute together with those ones that don't have the control, because the control they don't have the attribute. The control together with those that don't have the attribute on the experimental side. I get the one that have the attribute on the experimental side and now run it. That's the only thing. But if it's going to do separate regression, you cannot do separate regression for control and do separate regression for experimental. You can combine it together. You just want to, it's possible because the same factor, maybe somehow, it just happened that the factor it does not vary, the attribute does not vary on the control side, but it varies on the experimental side. But when you collab all of them together to do, so you still have yes or no of that attribute. I don't know if there's any other, I don't know if I have answered your question. Any other one? Any other one? So if there's no question, so that I can just stop recording, we can discuss some other things, extracurricular things. Because the whole central curricular, I would not like to record them so that it just make the video to be cheap for nothing. So if there's any question, please quickly ask a question before I stop recording. Because any question you ask, or people benefit from it, I want to record it so that I can record the response also, so that you can benefit from it later. Okay, if there's no question, let me just pause.